Okay, we will start. Hi, everyone. We are continuing with the series of ACRC webinars. Today, I'm very happy to have Professor Anupam Chattopadhyay from Nanyang Technology University in Singapore, NTU. Anupam is an associate professor in NTU. He did his PhD in Aachen in Germany, and he will talk about electronic design automation for emerging technologies. Anupam.
Yeah. Okay. Good morning, everyone. Thank you, Shaha, for hosting me here. And it's my great pleasure to give a talk at Technion, where I had the good fortune to visit once, and I enjoyed my stay very much there. And we engaged in some collaborative research, which I will also cover to some extent in this talk. And this is part of this IEEE Council of EDA Distinguished Lecture, and where I'm now included to give a talk on this electronic design automation for emerging technologies. So this talk has two parts. One is where I will focus on in-memory computing technologies, and in another part, I will talk about quantum technologies. So to give a brief background about myself, so in our group in past and present, we tried to connect several quadrants, I'd say, that we looked into algorithms, design automation, system design, and technologies. In algorithm, I have worked in the past in wireless receiver, wireless communication applications, and cryptography and security, numerical linear algebra, bioinformatics. In technology, we have been predominantly working in CMOS, but with the emergence of new technologies in memory computing and quantum computing, which is the focus of this seminar. I have been looking into this in collaboration with domain experts. And this eventually, this algorithm is realized into some form of system on chip, ASIC, reconfigurable processors, coarse-grained reconfigurable architectures. And this whole flow is enabled through very efficient automation tools like ASIP synthesis, ASIC synthesis, domain-specific high-level synthesis, logic synthesis, and technology mapping. So sometimes this is remaining at the background, but the design automation flows play a very, very crucial role in order to bring the advances of the applications and the advances of the technology together to give us the systems that we use in our day-to-day lives. So during my PhD, I was working on high-level synthesis flow for microprocessors, which was primarily looking into wireless receivers. And at that time, we faced certain challenges on mapping mapping this efficiently on various kinds of application-specific architectures. And from that background, we figured out that one problem that we continuously face is the data bandwidth problem for architectures. And one of the works that we did was in the context of matrix operations. And this is a particular design of coarse-grained reconfigurable architectures where you have a crossbar structure of multiply accumulate modules. And it was already established before, and we actually showed it again by experimental studies on actual designed CGRS structures, that if you are mapping it properly in the row-wise and column-wise inputs, then you can perform a matrix operation in basically linear time. So as we all know, that theoretical complexity of matrix is order of n cube or slightly less than that. And here we basically do a trade-off by putting this square element here, and this n square part of the matrix operation is going here. So basically you get a 4-cycle multiplication of 4 cross 4 matrix. So this kind of problems are abundant in wireless receiver and later in cryptography, in bioinformatics, and very recently in machine learning. So from this background, we started looking into what kind of architectures are most suitable if we try highly data-driven applications. So CGRA was on the first cut, but even in the CGRA, we figured out that there is a bottleneck happening because you have a limited data bandwidth at the whole system level and the input output level. And also you cannot arbitrarily pass the data between different points. That would simply make the whole network more complicated. And this is a topic that people have taken up in detailed study in the network on chip research or NOC research. So in the same vein, we actually did some more experiment and we came up with a very innovative architecture, I would say at that time. It was in 2011 and 12. So what we did is we figured out that the CGRA, where we are facing the data bandwidth, we can decouple the computing layer from the communication and from the storage layers. So we created a layered architectures that we call as layers, where the layers could be virtual or it could be in physical plane as well. So during that time, the 3D IC design was also growing in prominence. But unfortunately, we didn't have access to the technology to make these transitions very fast. So at that time, the through silicon vias were available, but through silicon vias were taking a lot of area, and the data transmission that could be done through that was not really up to the mark that we needed. So we did everything at that time using the existing semiconductor technology. And even then, we figured out that we are getting much better energy efficiency and performance compared to a plain CGRA, or also in comparison with GPUs. So we were benchmarking data-driven applications like linear algebra libraries, and we mapped it onto this layered architectures. So in this layer, the computation is happening. And when the computations are being done at the same time in parallel, an user can keep on reorganizing the data that would be needed for the next wave of computing. So that's what's the beauty of this multi-layered architecture. And this reorganization part can be completely user controlled. So we have a configuration bits for the computing as well as for the communication. And that is, though it brings us a lot of performance efficiency, it also makes programming of such architecture much harder. So to partly elevate this problem, what we did is we created a parameterized linear algebra library. So you just need to check, like, I want to do Givens rotation, I want to do matrix multiplication, householder transformation. You have to give certain parameters, like what is the dimension of the computing block, what is the dimension of this communication and storage elements, and what is the dimension of the actual matrix that you are trying to map here. Of course, the size of the matrix would be much bigger than what you will have here. And with that, we could build up a set of libraries, making the programming part considerably simpler from the high-level application point of view. So this was the kind of background work that we were building. And around the same time, we came across these innovations of HP and this memristor kind of technologies, and turned out that we can actually do much better, and we can go into the full processing in memory. So in that case, it's not necessary anymore that you build up a CGRA or highly parallel architecture, but you can have a crossbar and you can put your computing blocks, though in a very small form factor, in the crossbars. And the first time I learned about it, it was very fascinating. And I think for every researcher, it's a very interesting moment that you see, okay, now this immense capability from the memory devices are unleashed, and you can do many things about it. So we were thinking that what could be done. So of course, you want to connect it to the application level. And one way to do that is to make it as general purpose as possible. So around this time, we came up with some architectural ideas that we will have programmable logic in memory architecture and programmable logic in memory architecture with exposed parallelism like VLAW structures. And corresponding to those, we developed some programming models and synthesis flows for these architectures. So none of these were still tapped out because we didn't have the fab capacity or go with a large crossbar. So those technological challenges were being addressed, but we were trying to stay a bit ahead of the curve and figure out what would be the best model for creating this in-memory computing flows, what would be the synthesis challenges, how should we address this. And at that time, we were also experimenting with some very special kind of devices which could have not only memory capacity, but it would have multi-bit memory capacity. And we tried to push the envelope by saying, okay, if there is a multi-bit, then we can also perform ternary arithmetic directly on the memory, or we can perform fuzzy logic realization directly on the memory. And at that time, we were having some collaboration with this group in Aachen and Jülich, who helped us with very simple devices, like you can see 3 devices, and we could perform some basic ternary operation. And that showed that there is a feasibility study that it's possible. So this basically get us on the set of, okay, what can happen within memory computing, what kind of architectures are doable, and what is the possibility to make this more mainstream. And this is just a glimpse in the background of how we entered in the field. And now I will talk about, specifically in processing and memory, 2 different things. Why we want to do this, and what kind of design automation challenges do exist, and what kind of solutions we propose for that. So coming to the why part in processing and memory, that we know all from this existing von Neumann bottleneck, that there is a CPU part and the memory part. In order to perform a computation, you always have to bring the data from the memory to the CPU, do the computations. So this was all fine that you are addressing some bandwidth bottleneck, but exactly what savings are happening, this needs to be quantified. And one way to do this is, of course, to get more and more use cases and application level case studies, some of which is done very nicely in the group of Shahar in Technion. But I think to make it, say, more scalable and to apply it to any kinds of application and algorithm, it would be great to have it in a more abstract flow. And this is something that is also was driven by Shahar's group and in Ronnie. And I was fortunate to take some part in this study. So I will give a background of that here in order to give a clear picture why we need this in-memory computing and what is the most pressing argument for that. So what we did is, together with Shahar's group, is to come up with a study for the processing and memory performance. And we were trying to build an analytical model, a model that we call as the bitlet model. So in the bitlet model, you have some basic parameters, like you say, what is the operation count, the number of basic gates to need a particular computation. And there are some basic examples of operation count, like if I have an n-bit full adder, then the number of NOR gates that I need to do it for is 9n. If I have multiply operation, it's 13n square minus 14n. Of course, this varies between various implementation styles, but you can definitely get a range. And for each of them, you can exactly put the numbers. And that can be plotted nicely, that if I increase the operation size, like the input operands for this particular Boolean operation or arithmetic operation, or even more complex operations, you can see how the operation complexity is growing. So for some, the growth is very slow, like basic Boolean operation. And for some of this, like multiplication with higher precision, you can see the growth is extremely fast. So that's the first thing that we bring into the picture. And then in the bitlet model, there are some more parameters that are put, like what is the operational complexity, then what is the cycle time for performing a PIM operation, and then there is what the count of the memory array that you have in the memory, and what are the dimensions of the memory array. So you can have multiple separate memory arrays, and you can have a large memory array. So all of this forms different parameters in your overall model structure. And you can also see that how the parameters are related to the fundamental trade-offs that I am having an operational complexity that is arising out of the algorithm. If you can define a better algorithm, the complexity may reduce. Then there are some technological challenges, that how much time a PIM operation is taking. architectural challenges like how many parallel memory arrays I can accommodate in my system. Technological challenges, how big the array could be for a pin structure. And from this, what can be done is you can see this ratio, that what is the number of parallel computations that you are enabling in the processing in memory block divided by the latency of single computation. And that gives a very absolute number in terms of these parameters, that throughput or PIM is equal to the rows multiplied with the number of MADs, the operational complexity, and cycle time. This is the numerator and this is the denominator. So if you have more number of rows, then you can have more parallel operation being done in a particular array, and that will definitely improve the throughput of the PIM. Similarly, if your operation count is less, that means your throughput will be again higher. So that is the end-to-end throughput for a complex operation. And with this background, a lot of very interesting studies with various parameter changes was done, which you can see in detail in the paper. So I will just give example of two studies. So if I look into the PIM performance from the number of MADs and operation counts, then you can see they are always forming a curve like this, that if I have different PIM configurations, like I have a 16K different arrays or 4K different arrays, depending on that, the throughput will change. And similarly, if I vary this in operational complexity in the x-axis, then corresponding to that also, the throughput will keep on decreases. If the operation complexity increases, then the throughput decreases. So you can fix certain parameters and keep varying other parameters to get a clear PIM performance trend. And some other numbers were kept fixed here. So just for the representation and ease of understanding that how things are changing. Now, if I look into the same thing from the CPU's perspective, that, okay, I am fine that I will bring all the data from the memory to the CPU, do the computations in the CPU and send the data back to the memory in a typical von Neumann fashion, then what is happening there? What is the performance that they can achieve? And there, the assumption that was made in the bit-rate model is the memory bandwidth forms the only bottleneck of the CPU performance, but the computation that can happen in the CPU, it's so dense that PIM cannot likely compete, because you basically form a series of computations back to back, packed with each other. And this technology for the CMOS operation that is being done here is also more advanced compared to what a basic NOR gate in the PIM can achieve. So CPU has the technological advantage. It is developed over many decades, where PIM started developing now. So if you right now compared to PIM, CPU will have some advantage in computation. But on the other hand, the CPU computation, it inversely depends on the data in out. Because if you need to transfer a lot of data, then the CPU needs to really do it very fast in order to justify the transfer of this data. And this is something that can be quantified in terms of this parameter that we call as DIU, or data in and out. And here the CPU related parameters that are taken from the standard microprocessors, that you see the memory bandwidth is typically an architectural parameter that varies from some TBPS range, whereas the data in out, and that is then again an algorithmic parameter. You can have certain values. So this can vary depending on what parameter model that you want to introduce. So the CPU throughput compared to the PIM throughput is actually independent of the operation, and it is completely dictated by the ratio of bandwidth versus data in out. So if we put this, then it's very clear that the CPU performance improves when bandwidth increases or when the data in out decreases. So you can put different bandwidth parameters, different data in out parameters, and based on the operational complexity, you can see how the CPU throughput actually jumps from one plane to another plane. So then what was done in the bit-rate model is this was superimposed with the PIM throughput model. So given the same task, what one can do is model this for the CPU performance and model this for the PIM performance. And what is clearly observable then is that there is a crossover point. And this crossover point depends on, of course, all these different parameters. But if we fix the parameters, then it can be the operational complexity. If I fix the DIO, PW, MATs, and other, say, cycle time parameters for the PIM, then we know if there is a particular algorithm which has an operational complexity of 612, then beyond that, we will know that the CPU will have a better performance. And below that, PIM will have a better performance. So intuitively, the reasoning is like this. If I have to perform a lot of data movement and do a very simple operation, then I will rather do it in the memory. And if I have to do a very complex operation and a little bit of data movement is needed, then better do it in the CPU. So this creates a very strong argument in favor of PIM. And in this particular context, bitlet model serves as the first model where you can see clearly that there is a trade-off and we may stand to benefit by integrating PIM in our SoC structures. And now this can be extended with the various PIM configurations, which can include, say, basic neuromorphic operations or analog PIM models where you have this MAC operations being performed. And then one can keep developing the system level software where in the same way currently we are handling a system on chip, application partitioning, or CPU GPU mapping. So we can also perform a CPU PIM mapping, that what kind of operations we have, how do we partition the application, where we put it, and how we map it on the PIM structures. So this was the scenario, but of course there is a lot of questions that is it practical? Do we have a fab support? Can we get the complete system designed with the PIM model and so on? And for that, a lot of very interesting studies were done starting from 2016, where the NeuroCube was one of the prime examples that used the logic layer of hybrid memory cubes. And in this case, it was not really doing processing inside the memory, but we call it processing near memory. But even in that case, this argument in terms of the bandwidth stands strong because you use the logic layers of the hybrid memory cube to save a lot of data transfer energy. Then in a very interesting development, there were some studies which was done for not only emerging memories, but existing memory structures based on plain CMOS technologies that you can perform bulk bitwise and or operation, and that could improve the performance compared to HMC by 9.7x. So this gives a rationale that at least for some application scenarios, if you don't do processing near memory, but you do processing in memory, then you may stand to get one order of magnitude. And of course, this trend is continuing because you now have even more powerful analog in-memory computing techniques, where it was clearly said that there are breakthrough AI chips, ML and AI as one of the main application drivers that operations perform there. It requires a large amount of data, which rather be stored in the memory and be performed in memory instead of taking advantage of the CPU there. So with this backdrop, parallel trend started is, let's say we have the PIM and we have the capacities. So how do you map a given application onto the PIM? So clearly the compilation and synthesis, all these flows needs to be built in. Otherwise, this technology will never be there because users always prefer the convenience of high-level programming. You may give them a supreme technology, but if it is not controllable or programmable, then it's very hard for someone to accept this. And this is the domain where I started looking into. So what we figured out that it's not only a single technology, but PIM is being supported by DRAM, STT-RAM, other emerging memory technologies in ReRAM. And there were a lot of nice studies which were done to show that you can realize a lot of basic Boolean operations into these technologies. And the first operation that was done in the study of HP in 2008 was in fact material implication. And when they were doing the studies, they also made sure that whatever logic that is being realized is universal, functionally complete, because without that, you won't be able to map all sets of Boolean functions onto that. But it's a very rich set of logic family. Like you can have majority gates, 2 input, AND NOR gates, imply function, Boolean majority with negation, not 2 gates. So now if one looks into these native functions and their eventual realizations in different circuit structures, one may say, okay, these functions and this particular basic logic building blocks were already studied in CMOS. So what's special there? So why we need another set of design automation flows in order to address this? So there are actually 2 reasons why it required a lot of new research to be done. The first is, in CMOS, the predominant logic operations are done using NAND, NOR, and a little bit complex gates. But to do the logic synthesis and operations with other sorts of gates like majority, implication, this was not yet mature, I would say. And the second reason, which is a more pressing reason, is in CMOS, the technology mapping works in a very different way, because you can organize the logic gates after synthesis in any form that you desire. And then what you can do, you can simply do a place and route and you can tape out that particular design. But in case of in-memory computing, what's happening is you are already given a structure that is a crossbar, and you need to map this logical operation into that structure, as well as you have to remember that if the operation is done, the data is being stored in a particular device or a particular row and column, which will be reused. So you are overlapping the storage and computing. So which is somehow attempted in FPGA logic synthesis, because in FPGA, the structures are also some similar. But in FPGA, the basic building blocks are different. It's lookup table based. And here the basic building blocks are different. Also in FPGA, you can group larger operations together, and then you can form the blocks. So the granularity is much more coarse. Here in PIM, the granularity can be much more finer. But even then, as I will talk later, is we actually reused a lot of ideas from FPGA synthesis flow in order to get the best synthesis results and technology mapping results for PIM. So in the following slides, I will describe a bit of how synthesis and technology mapping is attempted for PIM and how it improved over time. So for any EDA flow, we start with the design specification, which is in a high-level language, and then we move towards the logic synthesis flow, and finally the technology mapping flow. A logic synthesis flow is still in a technology-independent abstract representation with logic, which can be in form of AND inverter graph, AND OR graph, or majority inverter graph. The inverter is needed here because it gives the completeness to the set of Boolean functions. And then once this synthesis is done, this graph is mapped to the final crossbar of memory, which has their own technology limitations. Like if I have a majority operation here, and if I see that the crossbar is supporting NOR gate, then I need to figure out how to map it there. And also the placement of operations play a very important role. Like as I mentioned, the placement it's needed to consider that you are storing the result and then you are going to reuse the result in the following or after a few cycles. So this is a very basic majority inverter graph for logic function that you have multiple levels. These are input operands and which undergo some majority operations. So majority is a 3 input operation. And after these operations are done with these 2 levels, you get the final output. So when we transform a given specification to a majority inverter graph, in logic synthesis, the goal is to convert this input graph into some resulting graph to optimize certain criteria. Like it could be the reduction of the number of levels, reduction of the number of vertices, because though it's still abstract, it has some correlation that if I have less number of levels, I will have to perform less steps. If there are less number of vertices, that means I will probably use less number of devices. So this loose correlation already is evident at that level. And in order to do these operations and manipulation of the logic structures, there are a set of academic as well as commercial tools that are available, including ABC, that's a tool developed in Berkeley, and CURD, that's another logic level synthesis tool. These tools not only support the logic level optimization, but also verification, which is very important because you start with a high level specification, and after every optimization, you need to check if your optimized graph is still performing the same functionality or not. So the second part of this EDA flow is to do the technology mapping. And in technology mapping, what needs to be done is to determine a sequence of low-level instruction that you can apply to the crossbar array. So in this case, since we are talking about mapping the operations onto processing in memory, so we assume that we typically have a crossbar array with rows and columns. So when we say the sequence of instruction, then we need to apply certain voltage to this individual rows or columns, depending on which underlying memory technology that we are talking about. It could be something coming from DRAM or spin-based RAM or MRAM or RRAM, but all of them have their unique application points for this low-level instructions. So that can be directly generated after we perform the technology mapping. And once we do the technology mapping, the exact delay and area of the final system, the PIM system, can be figured out. And sometimes there are considerations like you can do area constraint technology mapping, where one may say you have a fixed device count and you have to map using that, or you have a fixed dimension of crossbar and you have to map according to that. And this is a standard technology mapping flow that we did apply starting from a Boolean function. You can perform the logic synthesis using AND inverter graph or majority inverter graph. And then if there is an area constraint mapping, then it is providing some inputs like there are K devices available, or this is the crossbar dimension. And based on that, there is an internal operation that happens using lookup table based synthesis flow that I will explain in the following slides, which checks if the mapping is feasible or not. Because when I have a fixed device count, the feasibility check is important. If not, then we have to update this and then keep on iterating until we get a completely feasible mapping. And then it generates the final instruction. This gets an area constraint mapping. On the other hand, it's possible to also get a delay focused mapping, where instead of trying to minimize the device or adhering to certain dimensions, we try to parallelize as much as possible. And when we are doing parallelization, then it's better to form intermediate blocks where a lot of devices can be packed together so that you apply one single voltage and then a lot of majority or NOR operations, they happen in a single cycle. And this packing technique is crucial in order to reduce the delay. So this is the basis of the logic synthesis flow and technology mapping flow for processing in memory. And now I will go into a little more detail of what kind of optimizations are done in order to get the best end result. So here is one such example that what we did for the technology aware logic synthesis. So in the majority inverter graph, one standard flow is to do the majority refactoring, followed by Boolean partitioning, algebraic rewriting to obtain the optimized MIG. Now, the optimization criteria for the traditional logic synthesis flow is to reduce the depth of network and number of nodes. And for PIM, this alone is not sufficient because we may want to also completely utilize a given crossbar dimension and pack as much operation in one row, for example. So this is what is done in Revamp, this VLAW style PIM platform, where we looked into the majority inverter graph and we tried to refactor the majority structures in such a way that we have one node that is a common ancestor node to many majority nodes here. So in this case, clearly when we are mapping this structure onto a crossbar PIM array, then we see that this individual operations where S1 is the device on which we are going to apply the majority, the B1, B2, B3, B4, all of them can be applied as column, and this W can be applied as a row. And since this is one common ancestor to all the majority operations, we can apply to one single row and pack all the devices here. So this kind of manipulation, if I can figure out more refactoring techniques to obtain such common ancestor to multiple majority nodes, that significantly reduces the number of steps in the end PIM processing. And this is one way that you can perform a technology-aware logic synthesis flow. This is very common in CMOS, and this is one thing that we identified that can benefit the PIM structures. So this technology constraints actually come from the device and its own uniquenesses, which can be propagated up backwards to the logic synthesis flow. So there are other technology-specific logic synthesis flows also has been proposed for PIM. Now, going along this line, so as I mentioned earlier, the closest logic synthesis flow to PIM structure is based on FPGAs. And in FPGA, the standard way to perform a logic synthesis is to basically start from MIG or AIG-like structure and then perform some cuts, or they call it like KLUT, logic cones, because in a particular logic cone, if you have a single output and if you have K inputs, then all of this can be fit into a K input, one output Boolean function. Now here is the example of a 2 input, 1 output that can form in a 2 LUT structure. And these 2 LUT structures can be directly mapped onto a crossbar. So in order to take advantage of some LUT-oriented logic synthesis flows inspired from FPGAs, so we defined something called a super gate, and we call it a super gate aided logic synthesis, where the entire flow from the synthesis to technology mapping is guided by the LUTs. That you start from an logic level representation, make the lookup table LUT cuts, and then these LUTs, if I represent them in the Boolean tables, then they can be almost one-to-one mapped to the crossbar. That I have these results here, I put this into 2 different rows, and they get these 2 different outputs that I have here. And in the next iteration, I need to copy the outputs to again 2 rows, or I can even drive the operations in column wise. So that also gives a very fascinating way of taking the logical steps one after another in a crossbar, that you can perform a row-wise operation followed by column-wise operation, and so on and so forth. So here is a bit more detail on the super-gated logic synthesis flow, where the intuition is to start from an AIG or MIG-like flow. Then you convert that into an LUT-based circuit, where the size of the LUT is something that you may configure. And we actually took the example of this magic memristor crossbar, where it can be theoretically used up to n NOR with n greater than 2. And then you use the logic level LUTs in parallel, exploiting this magic crossbar. Then you need to finally convert that LUT into sum of product form, because it eventually goes into a NOR inverter logic. We start from a logic level representation, LUT level representation, And then given the crossbar dimensions, you basically simply put this one after another as blocks. So this is a very basic technique from the logical manipulations, how we can convert into a sum of product forms to NOR of NORs in the LUT. So if I have a 2 LUT, then a basic sum of product form can be like this. Then since magic is supporting the NOR and NOT operations, you can perform multiple complement in order to get a NOR representation, where each of them are your NOR ones followed by your NOT 2. So you have a NOR 1 and NOT 2, and the NOR of NOR LUTs. This can be mapped onto the crossbar, which supports the basic NOR operations. And similarly, this can be mapped onto other crossbar which may support NAND and NAND one after another, or it supports imply and invert. So it's the technique is always that you start from an LUT and you distribute the LUTs in the series of operations that is supported by the underlying technology. So in this case, the sum of product LUT form was like this. Then once you get in a NOR of NOR form, the resulting LUT was like this. And the magic crossbar gives a very simple one-to-one mapping onto this, where I have these operations laid out in rows. Then the result is obtained in a column after these 2 rows. And then you finally perform the end inverter NOT to get your end result, this M35. And that can support a full LUT cone operation. And in that mapping, you can reuse the old FPGA synthesis flows only to be adapted to the memristor crossbars. So this is basically the timing structures of this. And this shows how the operation flows in this rows and column orientations. And this can be done with this 3 cycles in this logic formation. And we kept on working in this direction. And one of the results that we also obtained is once you are giving some crossbar dimensions, then you need to think of how to put the LUT placement and then reuse the operations internally. Because you start from the LUT graph generation that can leverage from the open source ABC synthesis flow. But then you can get stuck because once you're mapping this, your crossbar can be completely full. So you need to reset certain elements to free it up. You keep the intermediate values, and then you again have to do the LUT placement. The LUT placement is always keeping you the row and column dimensions in the input parameter and the spacing that needs to be done in order to take the operation flows. And one interesting sub-problem here is to figure out how to best align the stacked LUTs so that you can minimize the amount of copy operation. So every time if operation is being performed in the PIM, that you are producing a result that is being stored in a device, and this result will be needed in a follow-up operation. So now for the follow-up operation, it might not ideally be located there because the operations are being produced in different parts of your complete crossbar. So you need to bring them together. And that requires you to finish this A* search operation, which can be performed in order to reduce the copy operations. Then we eventually result this, generate this magic instructions for the crossbar structure that Shahar proposed. And we showed that you can considerably reduce the amount of delay while maintaining the crossbar dimensions. So this is basically one slide snapshot of what is happening in the PIM synthesis flow, that you start from the input functions. There are some very nice and large benchmarks available for always comparing your results and improvement compared to the previous synthesis flows. That goes to the logic synthesis, which can take the forms of AIG, MIG, LUT graph, and then there are technology mapping operations, some of which was done together with the collaboration with Shahar's group. And he's one of the of course, most prominent researchers in this domain. So this could be taken to some computing memory architectures like revamp or AMMPU. And this is where the problem statements are lying right now, that we know how to develop, and we develop tools which are available for free, downloadable, to create the mapping of a given Boolean functions or some arithmetic operations onto a prim crossbar. But now if we start thinking of the PIM to be part of a bigger system, then what are the practical demonstrations that can be done by adding the PIM together with the CPU, like a RISC-V core or something like that? What would be the OS and compiler support that's needed for an user to take advantage of some pre-synthesized libraries, or to do a high-level partitioning, considering the data bandwidth and eventual improvement that the application can gain by having this PIM flows. So this is about the first part of my talk, and I will now move to the second part on what kind of EDA problems are coming up in quantum computing. So you may interrupt me now with some questions. I have my chat window open, or you can also ask the questions together after this discussion. So in quantum computing, of course, the first question is why we need quantum, and how practical it is, and what kind of design automation flows are needed. So for the first part of why quantum is needed, so there are a lot of research and commercial activities in quantum computing domain. So there are quantum computers which are all right now available for selective research usage, or you can also apply for a cloud level quantum computing access. These are relevant to security threats that I will elaborate in the following slide. And there is also a lot of activity in very special purpose quantum computing devices, not like fully general purpose processor, but more similar to an ASIC that is designed to solve hard optimization problems. And these are commercial and available for people to purchase. And they have solved some problems like simultaneous annealing, quantum Monte Carlo, and demonstrated speed up of selective parts of a data set, but they are practically useful. So it is there and it is coming up, which clearly shows that engineers have now the capability to take advantage of the quantum physics to perform meaningful computation, which was envisioned by Richard Feynman. And this is a summary study that was published in 2019. It's called Consensus Study Report, which brought into picture that, okay, there are certain algorithms like Shor's algorithm or Grover's algorithm developed specifically for quantum computers. So these are quantum algorithms, and they can pose real threat to some crypto systems like RSA or elliptic curve cryptography. They can be broken in a matter of hours if we have a large enough quantum computer. So this was one of the first wake-up calls for the engineering community and the security community that, okay, if I can build this quantum computer, then I need to rethink security. So that means this is an important problem. If I don't build it, someone else will build it. So a lot of people actually came together, and it required innovation across multiple levels in the algorithm, in the technology, in the device integrations. And there are many different competing technologies which demonstrated that they can create a quantum computer of reasonable complexity. And right now, one of the challenges that people talk about is, okay, you say that you can break RSA using Shor's algorithm, but that requires like few million qubits. So where are we now, and why should I really care about that? So what is the gap? And for that, people often quote that, okay, the CMOS also have gone through a significant, say, increment in the complexity over multiple decades, which was driven by Moore's law. And similarly, we are also seeing a growth of the complexity that a quantum computer can be built with. And some people are dubbing that as a Nevin's law, following Hartmut Nevin, who is leading quantum computing efforts in Google. So there was a particular article by Nevin where he showed that we are also observing a significant growth over the years. And if this follows a similar exponential growth like Moore's law, then there is no reason that we will not have a quantum computer to break crypto systems within a decade. And this is fast growing. So of course, we always use the security as one of the first examples, but then it turned out that there are other application areas which can also benefit tremendously from quantum computers. And before I go into that, I will just cover a couple of slides to give the basics of what is in a quantum computer. We have this qubits, where this forms a building block of a quantum computer similar to the bits of a classical computer. But unlike a bit, it can be at 0 or 1, or it can be in a superposition of 0, 1. There are multiple technologies that demonstrates that qubit is achievable with sufficient longevity in the superposed states. This is the structure of a superposition that's represented in a block sphere, that you can have 0, 1, or you can have a particular intermediate of basis states in probabilistic amplitude of 0 and 1. So these qubits are the building block on which we keep operating using quantum gates. So when we write a quantum algorithm, then this algorithm is eventually mapped onto a set of qubits on which the quantum gates are being operated. And what is a quantum gate? That you may have an input initial state of a qubit, then you apply some gate pulses, and you get a final qubit state. You can also get a lot of intermediate states. So you can build a series of quantum gates like that. And all these quantum gates, they can be represented in terms of some matrix operations. And there are some gates like Pauli gates, Hadamard gates, swap gates, then Toffoli gates named after Toffoli, and some gates are named after Feynman. We call it central knot gate or Feynman gate as well. So these gates can take an input quantum bit and they can apply certain pulse, which basically results into a matrix operations onto this qubit. Now, similar to the classical Boolean logic gates, we also have a set of gates in the quantum world that we call as a universal. And one such universal gate is a Clifford group of gates, which is not only universal, but they have very efficient fault-tolerant implementation in some quantum technologies. Now, fault-tolerant implementation, this plays a very important role in quantum. Although we have talked about reliability and faults in CMOS, but in quantum, it required even more, because the effect of noise on the quantum computation or the state of qubits is much more prominent. So to control it at that level, you always need to have some kind of error correction code or a fault-tolerant implementation, preferably both. So Clifford group shows that you can have an efficient fault-tolerant implementation, and that's why this forms as the most, say, common set of logic blocks in the quantum world that people try to map their circuits on. So this is what I was just talking about, is that we need to have not only quantum computing, but a robust quantum computing. Why? Because the quantum computing is susceptible to many small disturbances. I would say there could be error in gate control, there could be environmental decoherence, the measurement error, because there is a classical world, you enter the quantum world, perform the computation, and then once you measure, then you are getting back to the classical world. So when you are measuring, then there could be errors introduced there. The quantum bits, qubits, there could be loss or leakage error because of that. And this could be addressed with the help of a few techniques. One is to have a fault-tolerant quantum computing, and the quantum error correcting codes and error suppression techniques. And let's say when we say that I need a quantum error correction code, then I am actually adding further quantum data. So it's a qubits on top of the basic qubits in order to recover in case there is an error that happens in computation. So it's the same way that we use different kind of coding techniques to recover if we lose some data in classical bits. In quantum, there are also quantum error correction codes. And the error correction code is implemented using some circuitry for their error correction purpose. But this itself can also be susceptible to faults. That's why what we eventually do is we implement the error correction in a fault-tolerant manner. And there are techniques for this, which is like efficient codes, like concatenated codes or topological codes that are implemented there. And these are already demonstrated and practically implemented for quantum computers. Now, even despite of all these things, what we see is we are still in the range of say 50 to 100 qubits, because we have to solve the error correction problem. We have to get stable qubits with good fidelity. And at this point, there was a very exciting possibility that was suggested in 2018 by John Preskill that, okay, the quantum computers that we have now could be small, but they still might be able to perform something that goes beyond the capability of current classical computers. And this started the domain or subdomain in quantum computing that we call as a noisy intermediate scale quantum computing, or NISQ computing. So in NISQ computing, people started finding out that what could be the big high impact application. Like, can I do quantum machine learning? Can I do financial portfolio optimization? So we are not yet talking about, let's say, breaking RSA or elliptic curve cryptography, because we know that it will require thousands to millions of qubits. But there might be some applications. And this was actually the idea behind the whole quantum advantage and quantum supremacy demonstrations, that we can show with small quantum computers some application that are already getting better than the classical computers. So that will kickstart the adoption of quantum computer and bring in more funding and more research opportunities. Now, one of the key things to do that is I may have a nice algorithm for quantum machine learning, but if I want to fit that into a 50 to 100 qubits, that means I need to design a small quantum circuit that will use less gates, that will use less qubits, and that will pick up only clean qubits, not noisy qubits. And that will also follow certain technological constraints like nearest neighbor constraints that I will discuss about. So that means it eventually boils down to a very efficient mapping and design automation problem, because we are eventually constrained right now due to the advances of technology. And even in future, if we can get our hands on with thousands or millions of qubits, this is now building the flow of electronic design automation for quantum computers that can help to realize the algorithm in a very compact manner. So this is the background of why quantum and what are the quantum EDA challenges. And now I will talk a bit about the development and where we stand in terms of the design automation for quantum computing. So this is an extremely fast growing field. A lot of research activities is happening. So I will try to touch upon the basics, and then there are topics which needs to be further explored and developed. But one good thing about this, what I also probably would like to mention, that there are already commercializations in terms of quantum computers, quantum algorithm and software development, as well as quantum EDA offerings. So there is a lot of activity, not only in research, but also in technology translation. So there are commercial quantum computers that I already mentioned. So it's practically realizable. Like in the case of PIM, I was mentioning there are practical PIM offerings which can be tried out. Similarly, there are quantum computers that can be accessed with cloud, or if you have enough funds, you can probably also buy a quantum computer. And there are very nice open source synthesis flows where one can contribute and keep developing, benchmark their studies. So there is one from IBM called IBM Qiskit. There are quite a few, and these two are kind of prominent. And there is the stack flow that is from a group of researchers in University of Waterloo. So the way the synthesis flow works is that you write a quantum algorithm in some quantum programming language, like Q# or Project Q. Then this is translated using quantum compilation and eventually mapped onto a quantum computer. Now, this translation and its mapping is where the EDA part of quantum computer comes into picture, where one of the flows that is shown here was developed by Matthias Soeken and his group of researchers in Microsoft. Is they showed that if you're performing an integer division using different methods, then how would you go with the quantum computing automation flow? So they implemented their initial algorithms in Verilog. Then this was again synthesized using open source synthesis flows like ABC, which was mapped onto a level that is called as reversible synthesis level. So reversible synthesis is the terminology that people started using in the early days of quantum design automation. It's because the fundamental quantum gates like C0 gate or Toffoli gate, these gates are completely reversible. So if you start from the input, you can go to the output, and from the output, you can come to the input. So that required us to develop some logic abstraction for reversible synthesis. So there are different reversible synthesis flows that are now available and integrated in these tool flows, which gives a reversible circuit. And this reversible circuit needs to be mapped to the quantum level. So that means if you have, say, a Toffoli gate, then you need to eventually map it onto the Clifford group of operation. Because as I said, the Clifford group of operation is now almost de facto standard because of its efficient fault tolerant implementation. So now some basics of how it started happening, that we even have a set of Boolean logic operations. Like I want to perform an addition in quantum. Then I have a quantum adder that I can represent in Boolean logic in a truth table, or I can represent in a binary decision diagram. Then there were works which converted a Boolean truth table into reversible circuit or binary decision diagram to reversible circuit. And there were some nice progress over the years on how to perform synthesis with minimum number of extra qubit, that is referred as a zero ancilla synthesis. Very specific circuit optimization, like I would optimize just for adder, I will optimize just for integer division. Then there were circuits that were performed with very small depth, quantum circuits with a T depth. T is one gate within this Clifford group or addition to the Clifford group. So this T gate is what takes a lot of cost in the final implementation. That's why people try to minimize the count of T gates or depth of T gates. So with a T depth of 1, the quantum circuits could be synthesized. And this kind of results were developed by the researcher over the years. So this is one example, is if I have a binary decision diagram, that if I have F0 or F1, depending on the current variable xi, if it is 0, then F takes F0. If it is 1, then F takes F1. Now this is the binary decision diagram, a logic level abstraction that we have, which can be mapped onto the quantum gates, where xi, f1, f0, this could be assumed to be already available. That means they are coming from the previous computation. And based on the value of xi, you can operate on the f1 and f0, which are like qubits in this case. You can apply control not gate, control v plus, control v gates in some sequence in order to get the final output, that's f. Xi is the value that continues, and this particular qubit is not used anymore, and that's why it just remains as an empty. So there are techniques where people can also perform follow-up operations to make this particular qubit again usable. Otherwise, this at the output remains as a garbage. So you want to minimize the garbage during the computation. So there is some development here which figured out, okay, the best way to synthesize the from the logic level abstraction is you look into the AIG, you get a structural view, because an AND inverter graph already means that you have the logic ideas, that there are AND gates and there are inverter gates. So with this AND inverter graph, the mapping to the reversible gates and eventually to the quantum gates, it figured out, it was shown that it scales very well. Whereas if I go with a truth table like representation or binary decision diagram like representation, you can also perform logic synthesis at that level. These are not really scalable, but they help to minimize the ancilla. So you can have zero ancilla synthesis. So by combining these two, it was shown that you can have a mixed structural and functional logic synthesis, where again, you start with the logic level representation, you perform a symbolic simulation to determine what is the corresponding decision diagram or truth table view, perform the small zero ancilla synthesis from that particular logical cut, and then stitch back the logical cut into the bigger circuit. So in the bigger circuit, let's say, for example, here G is the small subfunction that I pick up. And for that, I can perform the decision diagram of truth table based synthesis, where I don't have the scalability problem because it's a small cut. And then I synthesize there without consuming any ancilla. Then I stitch it back into the bigger circuit. So by this, I can always achieve a trade-off that when I see I am unable to scale more, then I can keep on going back into the AIG flow. And if I want to minimize the ancilla, I can pick up small cuts, and then I can do the zero ancilla synthesis for that. And very similar to the PIM-based flow, interestingly, it turned out that a LUT-based synthesis also works very nicely for the logic synthesis of quantum circuits, because in an LUT, you have the functional view, that's a truth table based view. So again, you can start from an AIG structure or MIG structure, pick up the LUT cones, and if your LUT cone is small, like if you have 5 input or 6 input, you can have actually optimal quantum circuits for these small LUTs, because this has been studied extensively, and up to 6 input Boolean functions, the optimal quantum circuits are known, which can be maintained in a database. So you access the database, replace this LUTs with this, and keep on stitching in order to build your complete circuit, which eventually takes the forms of like this, that you have some input qubits, you start operating on that using different reversible or quantum gates, and you get the final output. So this is about the synthesis part. But now when we look into the second part of the design automation flow, it's a technology mapping. And again, similar to PIM, the technology mapping needs to take into account different constraints that come from the quantum gates. And one such early constraint that was identified by the quantum technology and quantum device researchers is that when you are performing some operation between one qubit and another qubit, then it's better that these two qubits are nearest neighbor in your final formation. So here are some example formations that you can already access and see in the current quantum computers. These are different IBM quantum computer formations. So if I have a 5 qubit quantum computer, as you can see here, these 3 qubits are nearest neighbor and these 3 qubits are nearest neighbor. Now I may have a 4 qubit operation happening in the reversible domain. If I want to map this into this particular structure, then I need to know if the first qubit is going to be mapped onto this Q0 or not. So this brings us to the mapping problem. This can be somehow simplified if I say, okay, when I'm doing the synthesis, I will do it in a way that it will be always completely nearest neighbor, already at that level. And this complete nearest neighbor achieving can be done by adding swap gates. So for example, here I see that this particular qubit is 2 qubits away from the target qubit. So what I can do is I can swap these 2 qubits. So that means this gets closer here and this gets closer here. And after this swapping is happening, even if I do this, which are far away, they are basically happening in the nearest neighbor fashion. But this is a problem. This was shown to be NT-complete. And this also does not take into account the various configurations here, because I don't need to achieve everything to be nearest neighbor. What I need to achieve is whether the circuit is actually mapping to the target quantum computer, and I need to respect its nearest neighbor constraints. And this nearest neighbor constraints can be varied from a quantum computer to quantum computer. They can have many different topologies. And this is a particular technology mapping problem that was addressed in many different ways by having look-ahead schemes, by having heuristic solutions, or could be shown also with depth-optimal fashion. You can do nearest neighbor mapping with ILP formulation, but that has its own scalability challenges. So currently some nearest neighbor circuit mapping are already integrated in the open source quantum design automation flows. So now this is not the only constraint. There are nearest neighbor constraints from the topology, but in parallel, there is also another constraint that was identified is when you are mapping onto a quantum computer, there are different qubits and all qubits are not equal, which means there are some qubits which can be more noisy, some less noisy. So it's better to map certain operations in certain qubits during the whole mapping flow. And if you have less noisy qubits, then this will give your end result with high fidelity. So if you have a group of low fidelity qubits, this can yield erroneous results. So to put all this together, when we had this technology mapping problem, we proposed something called Mukut. This Mukut has this technology mapping problems split into multiple phases, that you have an input quantum circuit, and then you have a quantum computer's topology graph. Let's say this is the input quantum circuit which you already achieve after your logic synthesis. And then you have a connectivity graph that is provided by the quantum computer. Like this is a 16 qubit mapping for IBM Q16 Melbourne. And these two are taken as the inputs, which you need to take through this multiple flows. So this I will explain in the following slides, this 4-phased mapping that is done here. In the first phase, what is performed is you extract the subgraph. That means when you have this given quantum computer topology, then you know that within that there are some T topologies and there are some grid topologies. So you extract a small subgraph, and then these subgraphs are used to perform the first level of embedding for the qubits. This embeddings, this mean that you have the input quantum circuit where you have this particular qubit called L1. Now L1 can be mapped to A, and L2 can be mapped to B, L3 can be mapped to C, and L4 can be mapped to D. But this particular mapping will result in a specific series of nearest neighbor operations in the follow-up design. So this initial mapping plays a very important role in achieving the final nearest neighbor circuit. So we can try a fixed number of attempts to get the k-vertex topology subgraph from the given quantum computer and embed this initial qubits from the quantum circuit to this quantum computer. So this is one particular mapping example, that if I take T, then I will have a mapping. If I take grid, then I will have a mapping. So this 4 qubits can be mapped to any portion of this quantum circuit. So which portion I am taking and which mapping I am considering, that will give me different performances. But of course, I cannot test it exhaustively because then I cannot scale. So I have a limited number of attempts and apply certain heuristics to guide the next level of technology mapping. In the next part, what we are doing is to generate an NN compliant circuit. So that means once we have this mapping that L1 is going to A, L2 to B, L3 to C, and L4 to D, I need to add the necessary swap gates in order to make this nearest neighbor. So now, as you can see here, that A and B are already nearest neighbor. So for this reason, when I am doing an operation between A and B, I don't need to achieve any further nearest neighbor operations. But when it is between, let's say, B and C, it's also nearest neighbor. It's between C operation here and B after this, that's also fine. And D and B is also in the nearest neighbor. So I need to apply the specific swap gates so as to figure out when the nearest neighbor operation is happening or not. So in the original case, the operation was between L3 and L1. So L3 and L1 means that I'm doing it between C and A. Now, C and A are not nearest neighbor, which means I had to apply a swap before and after this. Why after this? Because I then bring it into the previous configuration so that the follow-up operation that is happening between D and B, that still remains nearest neighbor. Now, as you can see, I need two swaps if I'm using the T topology, but grid topology has more nearest neighbor structures. That way I can use only one swap. So this kind of early design choices can be explored when I'm doing the qubit embedding and subgraph extraction. And after that, I can do nearest NN compliant. So here we just show it in a single one directional flow, but it's also possible that you can go through the multiple iteration. That after NN compliant circuit generation, you see that it's not really good. You go back and try out with another subgraph extraction, and you can do some more iterations there. Now, after the NN compliant circuit generation is over, then what we do in the final phase is to look into the fidelity aware mapping. And the fidelity of different qubits and their corresponding noise, this information is also available from the quantum computer, which we feed into this particular flow. And when it is about the, let's say, the T topology, I can actually pick up 0, 1, 2, 13, or I can pick up 1, 2, 3, 12. Both are T topology. In both the cases, the mapping is feasible. But which one I will pick up, that depends on which qubits are less noisy. So these choices also can be explored in the final phase of fidelity aware mapping. And once we go through all this, then we can see that you can perform it on a real quantum computer, do some experiments, get all the results, and try out various different topology graph, different window size, initial configuration, and eventually the benefit that you will get in the end result, which can be measured in terms of your circuit depth or number of qubits or the fidelity, can be significantly different between various different choices. So this is all that I had to actually talk about quantum computing part. So quantum computers are now accessible to researchers and to practitioners. It shows that there is a theoretical advantage for a range of quantum algorithms, and sometimes this advantage is already demonstrated in a small enough quantum computer that is practical now. So in order to make sure that we keep on leveraging these quantum computers, we need to develop very efficient EDF flows in this NISQ era. And of course, going future, we also need to keep on scaling it up. One of the challenges is to look into different technology constraints, make it robust, fix the errors in the faults and error correction flows. One may also look into aggressive optimization for very specific circuits. So for example, I want to know exactly how many hours it will take to break elliptic curve. That means I cannot just rely on the EDF flows, but I may want to manually optimize the elliptic curve implementation on a quantum computer. And this kind of studies are also being done a lot. So in case of crypto, it becomes the quantum cryptanalysis. in case of other application domains like molecular dynamic simulation, drug design, financial portfolio optimization, there are researchers who are trying to optimize it for very specifically, sometimes taking advantage of the EDA, but sometimes it's also hand optimized circuits. So with this, I would like to conclude my seminar. I acknowledge a lot of, say, very nice hosting and collaborations with different groups. And this is a particular photo that was taken long back when I was in Technion. And I also acknowledge a lot of research support from various agencies in this studies. So thank you for your attention. I will be glad to engage in discussions and future collaborations on these topics.
Anupam, thank you very much. And as you said, right, some of the things that you presented started or progressed while you visited us physically. So I hope that soon it will be possible for you to visit us.
Yeah.
If there are more questions, either through the chat or just unmute yourself. If there are no questions, I have a question.
Sure.
So you presented logic synthesis for processing in memory, and this is something that is done prior to the tape out, basically. You define what you want to execute and design hardware that supports that in the controller. Another approach is to have very simple primitives and give the programmer to build basically the function that the programmer wants to execute.
Mm-hmm.
Have you thought about that and the trade-offs between the two approaches?
So can you give one example, like what the programmer would like to execute in this case?
So for example, it doesn't really matter what is the technology, but let's say that we are doing magic or whatever, right? Like NOR gates. So one approach is in using logic synthesis. You're saying, okay, I want to add two numbers. Then through my tool, or maybe something more complicated, like one of the benchmarks that you showed. So you find the right sequence of operations and the mapping inside the memory. And then your controller can support only that.
Right.
And another approach is to say, no, I want that support only the NOR gates. That's it.
Mm-hmm.
And the programmer will write the sequence as part of the C code, for example.
And that is the compiler level gap that still exists. And this is what I was actually trying to point out at the end. So this partly depends on which technology or which platforms comes in the prominence. And I am aware of some researchers which is trying to put together, let's say, a DRAM based in-memory computing or even RAM based in-memory computing together with RISC-V CPU. And some of the prototypes are also available, probably from the Sonur Mutlu's groups and so on. And these are also available in the simulation. And of course, we would like to make this experience from the high-level programmer as transparent and as convenient as possible. And the way I see it's going in future is similar to what CUDA achieved for the GPUs. And we don't want people to actually go into the low level and write the current voltages for different rows and columns, definitely, right? But in the high level, there are two things that needs to be figured out that, okay, if I'm mapping that into the existing PIM component of my SoC, then what is the performance I'm getting? And does this justify also the bandwidth transfer energy following some model like bitlet? Then I can start making the partitions. From the high-level programming language, this can be achieved either in two ways. Either you have automated partition done by the compiler, Yeah, so this is something that is happening, let's say, in a multi-threaded, multi-core processing. Basically, you write the high-level code and the threading is taken care of by sometimes a compiler because it's very smart.
So you can use libraries, for example. You don't necessarily
Right. So this is the part which is currently missing, but it also, to some extent, like what you are doing, you need to give a more and more real platform use cases so that people get excited about it and start developing the rest of the flow. Right, and this is dominantly happening right now with machine learning, because there are a lot of analog PIMs which can significantly speed up ML, and possibly one quick thing that will develop in future is to have a complete PyTorch to PIM flow. Yeah, in that case, you can bypass a lot of compiler level things for general purpose PIM, because this Macs are being done and it's extremely fast, which iMake did with Global Foundries. So if they can connect it to the high level with PyTorch, then people will readily use it, and you can spend a lot of engineering effort at the low level.
Any other questions? There's a question in the chat.
Okay, let me look into it. So I think it's better to derive the instruction set to be in a more complex order, because the more basic instruction set that you have, it definitely makes it very general purpose that you can map everything from low level to more complex level. But if you have more complex functions, like directly a trigonometric function realized into the PIM structure, that would possibly make it more high performing onto that, because you are creating a block of a trigonometric function that's mapped very efficiently there. And right now, the bigger push from the PIM community that needs to become is to show that it's really high performance. If I make a general purpose PIM, of course, it's a very nice research and it can help us map anything onto it. But you need to show that, okay, there is a bandwidth issue and I can do better than CPU only stuff. So both are doable, but if I'm given an option, I would prefer to have PIMs with more complex functions, like PIM that is doing Mac. Similarly, if I can have PIMs that is supporting the full numerical linear algebra stuff, then I would have it. And possibly in that case, you can directly map a lot of CUDA benchmark functions there.
Any more questions? If not, Anupam, thank you very much.
Thank you, Shahar.
Great seeing you and hear you again.
Yes. Okay, so say hi to your team, and hopefully we will see each other sometime soon.
Yeah. Thank you.
Okay, thank you. Bye.
Yeah.